Okay, in this video we're going to determine what are called the initial conditions and steady state conditions of storage elements, and the reason we're going to do this is it's going to help us solve problems involving capacitors and inductors along with resistors and coming up with the exponential curves, okay, as far as what voltage or what current these curves start at and what final value, whether it be voltage or current, the curves end up at, and then also how long it takes in between both ends of the curve. The initial conditions being at t equals 0 and the final values being at what's called the steady state. So here we have, let's draw a line here. On the left side, we have the case of a capacitor charging over time. So you can see it was initially uncharged since its voltage is 0 at t equals 0. And then as time progresses, okay, this being t equals 0 here, okay, so on the left side of the line is the capacitor case, where as the capacitor gains stored energy over time, it's the voltage that builds up. And as we discussed last lecture, as that voltage builds up across the capacitor as it's charging, the capacitor current's going to decay exponentially. And then for the inductor, it's just the opposite. That, whoops, I didn't mean to do that. So for the inductor, it's just the opposite. Here, let me get rid of that. Let's see. Let's write that back in here. Okay, so for the inductor, when it's gaining stored energy over time, it's the current that builds up, and it's the voltage that decays exponentially. So to find initial conditions and steady state conditions for these initially uncharged or unenergized storage elements, all we have to do, is look at the voltage current relation at t equals 0 in steady state. So first, if we look at t equals 0 in the capacitor case, okay, well look, at t equals 0, the capacitor has 0 volts across its plates, and yet there's a current. Well, this is the same VI relationship as a short. Okay, if you remember from earlier in the class, a short has 0 volts for any current. Alright, so you see at this moment in time at t equals 0, the capacitor voltage is 0, and yet there is a current, some finite current. So we say that the capacitor, its initial condition is that of a short because it has the same voltage current definition as a short does at this time. Look, in the inductor case, it's just the opposite. See, because in the inductor case, at t equals 0, the current is 0, and yet there's a voltage. And you see that's the definition of an open, right? That the current is 0 for any I. Okay, so those are our initial conditions for initially uncharged capacitor and initially unenergized inductor. Now the steady state condition is when you look at 5 time constants, when the voltage for the capacitor has reached its final value and the current for the inductor has reached its final value. Okay, so now if you look at this time, you can see that now the capacitor has a voltage across its plates and its current is 0. So the steady state condition of an initially uncharged capacitor is an open, and it's just the opposite for an inductor. That for an inductor at the steady state, it has its final current, but its voltage is 0, which is the same voltage current relationship as a short. Okay, so initial condition, steady state condition capacitor, initial condition, steady state condition inductor. In both cases, the storage elements are initially without any stored energy. Now, I have a handout on Polylearn that summarizes what we just went over. See, the second row is the initially uncharged capacitor. The third row is the initially unenergized inductor with its initial condition, steady state condition. Now, resistors are always resistors, okay, no matter what time it is. Resistors, as we learned previously, don't have the ability to store energy. They dissipate energy as heat. And then these two, the last two rows of this handout show the initial conditions and talk about the steady state condition for storage elements that have some initial stored energy. So here, V0, that's the initial voltage across the capacitor that has some initial stored energy, and its initial condition is that of a voltage source of value V0. And the reason for that is due to the characteristic of a capacitor where the voltage across its plates can't change abruptly or instantaneously. So whatever voltage a charged capacitor has across its plates just before a switch changes at t equals 0, just after the switch changes at t equals 0, it's going to have the same voltage. And we can represent that characteristic with an ideal voltage source of V0. Likewise, with an inductor, it's the current that can't change abruptly. So whatever current an inductor has, initially it's going to have the same current after a switch changes. Okay, so just before t equals 0 and just after t equals 0, an inductor is going to have the same amount of current, just like the capacitor is going to have the same amount of voltage. Now, steady state, if you connect a resistive path at t equals 0 up to an initially charged capacitor, well, over time it's just going to give up all that stored energy to the resistance, and it's going to just be depleted of stored energy. Okay, and that's also true of the inductor case. However, a big difference between capacitors and inductors is that excuse me, a big difference between the storage elements is that if you have an initially charged capacitor and you totally remove it from a circuit, okay, it's not part of a closed path with resistance, well, that capacitor will hold on to that stored energy. There will be voltage still across its plates, okay, because even when a capacitor that's been charged is totally removed from a circuit, the charge will remain on the plates, and as long as that charge remains on the plates, there's going to be a voltage across it, because remember, Q equals CV, and if there's a voltage across the plates, that capacitor is going to have an electric field through the dielectric, and it's that electric field that stores the energy. Okay, is the mechanism of which the energy is stored. So you can receive an electrical shock from a capacitor that's been charged, even though it's completely removed from a circuit. But you see, that's not true for an inductor. An inductor, remember, it stores its energy through a magnetic field, and a magnetic field is formed with a moving current. So if you were to take an energized inductor and remove it from a circuit where it wasn't part of a closed path, well, no current's going to flow through that inductor, and therefore it won't have a magnetic field, and no magnetic field means no stored energy. So that is one of the big differences between the storage elements, is that once a capacitor has stored energy, you can remove it from a circuit and it still has that stored energy. But that's not true for an inductor. Once it's removed from a circuit, it no longer has current, so no longer has a magnetic field, so no longer has any stored energy. Alright, so that covers initial conditions and steady state conditions for our storage elements. Let's now see how we would go ahead and calculate what the stored energy, how many joules our storage elements were storing. So if we look at stored energy for a capacitor, well, first of all, this expression here is just our basic expression relating energy to power. Energy is just the integration of power, and we know that power is V times I. We know that the current for a capacitor is C dV dt. So this is, I'll put a subscript C for energy for a capacitor. So you can see that the dt's cancel out here. So now we're integrating with respect to voltage V, right? Because we got to change our limits here since the dt's cancel out. Now we're integrating over voltage. So this comes out that the energy for a capacitor is just half CV squared. Okay, where V here is the voltage across the capacitor. Okay, so VC. Okay, you may notice that this is the same form of an expression for kinetic energy. Right, kinetic energy is half mv squared, where v is velocity. Stored energy for a capacitor, same form, half times capacitance times the voltage across the plates of the capacitor squared. Now I'm not going to do it in this video because it's the same process, but on your own you should be able to prove to yourself that for an inductor we would get that the energy stored by an inductor is just half Li squared. So same form of an expression, it's just you can see instead of a C we got an L, instead of a V we got an I. And you'll see this often with capacitor and inductor equations, that for the same quantity the expression will be the same form. It's just wherever you have a C in your capacitor equation you'll have an L in your inductor equation. Wherever you have a V in your capacitor equation you'll have an I, okay, this is IL, in your inductor equation. And this is actually called dual or duality. Okay, same form of expression but different variables. So you know, often you'll hear that capacitors and inductors are duals of each other for that reason. Alright, well the next few videos are going to be problems where we're going to utilize all that we've been talking about thus far and solve first order circuits with either an inductor or a capacitor using a circuits approach